Sometimes the frequency response of a circuit is more important than looking at individual voltages or currents at a specific part of the circuit. LTspice can help you achieve this with its AC analysis function. Welcome to this LTspice 4 AC analysis video. I am your host, Simon Bramble. This video shows you how to perform a basic AC analysis in LTspice, as well as point out some capabilities you might not already know about. The circuit I've chosen is a simple, single-pole RC low-pass filter. The circuit is constructed as normal with a standard voltage source. Once the voltage source has been placed on the schematic, right-click over the voltage source, click the Advanced button, and in the AC amplitude box, select 1 volt. Click OK. This applies an AC signal of amplitude 1 volt to our circuit. By selecting Simulate, Edit Simulation command, and the AC Analysis tab, we can enter a start frequency of 1 Hz, stop frequency of 100 kHz, and plot with 100 points per octave. And our LTspice circuit is now complete. With a resistor impedance of R and a capacitor impedance of 1 over j omega c, we can go through some simple maths to get the transfer function to be 1 divided by 1 plus j omega c R. By clicking on the running man symbol, the plot window appears and we can probe the output voltage. Here we can see the output voltage, how it varies with frequency, with the left-hand axis as dBs and the frequency plotted on the x-axis. This is otherwise known as a Bode plot. The solid green line represents the amplitude and the dotted green line represents the phase. Clicking on the plot label brings up our cursors, and by moving the cursors to the 3 dB point of the circuit, in the bottom right hand corner we can see the 3 dB point occurs at 159 Hz, and at the 3 dB point we have a phase lag of 45 degrees. If you have several plots in one window, the phase plot can sometimes make the window look cluttered. To remove the phase plot, left click over the phase axis and hit Don't Plot Phase. To get the phase back, left click over the phase axis and click OK. Now the plot window does not necessarily have to show phase, it can also show group delay. The group delay of a filter is a measure of how much each frequency is delayed as it passes through a filter. The Bessel filter, for example, is a filter with a constant group delay and is used if we want to filter, say, a pulse, but still keep the pulse shape without introducing any undershoot or overshoot. The group delay of our RC filter can be shown by left-clicking over the phase axis and clicking the Group Delay radio button. Most of the time, the Bode plot is all we need. However, LTspice can also provide a Cartesian plot showing how the real and imaginary amplitudes of the output change with frequency. To select the Cartesian plot, left-click over the dB axis, and from the drop-down menu, select Cartesian. The plot will change to show the real component with the solid green line and the imaginary component with the dotted green line. The left axis shows the real amplitude, and the right axis shows the imaginary amplitude, with the I inserted against the units. We know that for a single pole RC filter, the 3 dB point occurs where the real and imaginary parts of the transfer function are equal in amplitude. Moving the cursor to the 3 dB point, we can see that indeed the real and imaginary parts are equal, and this is shown in the bottom right hand corner of the screen. Note that we're plotting the transfer function here, not the impedance, so at high frequency both real and imaginary terms tend to 0. Instead of plotting real and imaginary output voltages against frequency, we can plot them against each other to give a Nyquist plot. For a circuit to oscillate at a given frequency, we need gain in the loop at that frequency, as well as a phase shift of 180 degrees. A Nyquist plot gives a quick way of viewing the stability of the system by showing how the gain and phase shift of the system changes with frequency. To investigate Nyquist plots, I've constructed a slightly more complicated circuit. Here we have a single pole RC low-pass filter, buffered by an op-amp with a certain amount of gain. I've then repeated this circuit 3 times so that we can show the effects of a single pole, dual pole and 3-pole RC filter. Run the circuit simulation as usual and probe the voltage across capacitors C1, C2 and C3. Here we can see the voltage across capacitor C1 gives a nice steady roll off, the voltage across capacitor C2 gives slightly steeper roll-off, and the voltage across capacitor C3 gives even more roll-off. And at low frequencies we can see the effect of the gain of the amplifiers as well. In the same way as before, left click on the dB axis, and from the drop-down menu select Nyquist. If I move the cursors to the 0 real, 0 imaginary point, this neatly divides the plot window into 4 quadrants. So we can see here that the voltage across capacitor C1 lies in the first quadrant, the voltage across capacitor C2 strays into the second quadrant, and the voltage across capacitor C3 strays into the third quadrant. Probing the voltage across capacitors C1, C2 and C3, we can see that a single, dual and 3-pole filter gives us a Nyquist plot in the first, second and third quadrants as expected. For more information or to download a free copy of LTspice, please visit us at www.linear.com/LTspice. Thank you for watching, and I wish you the best with your simulations.